Hey everyone, welcome back to this channel, and today I would like to talk about the main feature of incoming DCS F35 module and the thing do with it and what can we expect from it. Alright, first thing for the most people caring about is the aerodynamic module and the RCS frequency board graphic and what does it actually shows in the game. I think that everyone cares about. And when talking about it, we cannot left its mass module. Oh, sorry for that. Sorry about it. The reference. I'd like to tell there's a lot essays about F-35's aerodynamic design or their frequency board graphic. I think the aerodynamic can just directly buy it from the private company because it's not classified or what. If they've been published, that means it's no longer classified or even classified. It's totally okay. And if they don't want to buy it or the price is too fucking high, they can just using AI based on that graphic and generate a vector graphic of the frequency response of the F-35's RCS. They can already doing that. Yeah, that you can see this code is typically the C code. You can just put it in the MATLAB and run it. Alright, about the aerodynamic and the flight control system and what can you do with it. And I will show you. The flight control system of the F-35, you can just directly see in it from the F-35's datasheet. You can directly find it. It's a multiple closed loop control. Yeah, you can even modify such thing in your MATLAB, in your Simulink module, because hey, there's a lot similar part like you're doing your PID control or such a lot of control method you have learned from the college. It's all about automatic control. And you can see here's a sum, here's a sum, and here's an integral part. And here is another transfer function. Here is a MATLAB block. And there's a lot of things they can just based on the essays on the internet and making a fully simulated closed loop control. Just give you this one. This is about the asynchronous modules simulation. Okay, let's run the parameters to it and I'm doing a quick simulation about it. Yeah. There we go. You know, when it comes to game, it's not about running this simulation in like 2 seconds. You need to run it all the time as the user playing the game. Here's is just a model. It's a serve module design. I mean the serve models Simulink math module or whatever you call it. Alright, let's move into another part. I think this is quite easy for the aerodynamic team because the most developers in the aerodynamic are the professor from the aviation industrial, because most of them is working for the private aviation companies. and they're doing jobs on maintaining the other aircraft, like the civilians aircraft from the Boeing and from the McDowell. Oh fuck, I don't really know how to pronounce that well. Alright, that's the aerodynamic module, RCS frequency baud graphic, and the flight control system. And now another thing we mostly want to talk about is about the databus and subsystems. Because most thing was in here, let me draw a graphic about it to help you understand it well. Alright, let's just call it databus, okay? More typically, I will give an example like the 1553. That's a pretty low speed one, because no one is barely for the modern military aircraft we're using such thing. I mean, like the Gen 4 fighters or Gen 5 fighters, they no longer using it. Okay. Yeah. Well, let's just give 3 devices on this databus. Oh yeah. I know what you guys want to say. Yeah, let's make it more officially. Any more official. Okay, this looks better. Alright, let's get into it. Because all the user's interface and all the components of an aircraft, all the system of it, is all on this thing, all on this databus. Like your flight control unit, your FCS, and your weapon system, like your digital weapon system, like the one in the A10, and even about your radar and your autopilot. Yeah, is another part of the FCS, but let's just give an example. Let's just put it here, because autopilot always come with radar. And let's talk about the design of all the thing in the real aircraft. Okay, so now we know we have a databus, or you can just consider it as a switch. Because when we want to using a databus, we want to each module, like here, each separate system can communicate through this databus. They can communicate to each other by this databus, so this is actually a switch. Alright. And what we need in this switch, okay, let's just give an example of the VPX system I designed in before. Here you can see, because most military aircraft was designed in that way. Let's draw another picture. No, yeah, let's not saving that one. Because we have to talk. Let's just talk about it. For example, here's a TGP part. Okay, TGP part. It have a raw graphic input, like the 4K camera at the 60 frame rate. That's just FP second, frame rate per second. And you want to transmit this data through the databus. Yeah, let me just write it. Oh my god. I'm sorry, I'm really bad at drawing such thing. And if you want to send those graphic data through the database, and what you need to do. Oh, by the way, here's another thing to let it in. Give me a moment. For example, here's a TGB part. TGB pod. I have the MDI input, yeah, which you see here, the MDI input, and it also need to go some IT logic to get into the FPGA. After FPGA get those binary data, like this, like where's the flame at? Like you know, we know, like a picture, they have a row, tons of row and column. If like the 4K one, I mean 4K resolution, there's actually 4,000 rows and the codes, and each of them have and every row and column, and like each dot, they have their 3 binary data, R, G, B, like this one, and each of them takes about 1 byte. That's kind of too much because that's yes, you can calculate that one. Yeah, let's just calculate that one right now. Here's the median byte, and then if we here's about the gigabyte. Oh, that's not gigabyte, that's gigabit. And here is a gigabyte. It talks about 50G. You know what I'm saying? That's insane, the raw data of the TGP thing, because he sent 15 GB for every second to this database. And the original design of the 1553 cannot take such data. Because I clearly remember the baud rate, most baud rate is running at 10 Mbps. Here we go. And you know what did the engineer do about it? That's why I say the most, the nowadays, yeah, I mean the nowadays, the nowadays aircraft is no longer using this thing because it's just too fucking insane for a database to take on this one. Because the 1556, this baud rate is even lower, than the local bus in your computer. Which you alright, let me explain this later. Okay. So what they do about the targeting part? Because you always found in the game the targeting part is always an option, like you said. in the F14, like the lightning part, they always have they need to add in some special devices to make it to apply in the CTR screen. Because mostly the TGP part is not from the data bus, they're not gonna go through the data bus. I mean, in before, and that just caused a lot of problem. Yeah, let's just talking about it. The one before this is that's all the aircraft in the DCS. The logic rerunning on. Yeah, that's about it. They just bypass the data bus. They're not using the data bus for it because it's too fucking. It's taking too lots of resources off the data bus. Yeah, that's the older one. But what about the new one? I mean, like this one. Yeah, we can using those for the raw data input, like using the SRIO directly from the FPGA. After he getting the raw data of the picture from the targeting part, and he can send to the DSP to reduce the space of the graphic data, then send it back to the FPGA and send it to the CPU. That's what we do in modern day. That's the design we're doing in the modern day. So that's typically that's the data bus for the modern design. And for other devices, like your GPS, let's go back to that picture. We're talking too much right now. I mean, for the modern one. Okay, let me just draw this picture more easier. Like your other device, like your radio, like your VHF, RHF. Let's just call it RF radios. Okay, your RF radios and your other interface, like your interface, like, yeah, those other subsystems of the aircraft, and your monitoring screens, multifunction displays, all included in this part. They are on this data bus. I mean, the modern data bus is way much more advanced. It's kind of like the design. Kind of like the design showing up here. It is using a CPU and a FPGA and a DSP. The DSP running as a assistance of the FPGA. So where is as a very the high baud rate data input is coming in, the FPGA will simply send those data into the DSP. After the DSP reduce the space, reduce the space of the data, and he just send it back to the FPGA, and the FPGA can decide which devices he gonna send out. He can directly send back to the PC or send back to the PC, and the PC can send it out through this switch. Yeah, that's just an example of the switch. You can find it. That's called PCM 53135. Yeah. Yeah, you can find this data sheet of one. So there you go. So you can send it out by this. You can send the data out to other devices on the data bus. So it's totally achieving a function like a switch, like a internet, like a Ethernet switch. That's all the thing about that thing, and I can show you the design. I don't filled it in before. Now let's ignore the polygon about the source wiring. Yeah, you can see that. And what can the ego dynamic do about the simulation? I think if they can actually find the design of the board, like the data bus board design of the F35 on the internet, then they can run an EMI simulation on this thing and find what's the issue and what's the problem with their with their switch, like in their database, and what can be happened when the database is loading on too much data, and what will represent to other setters of the FPGA or CPU, and that will cause some problem, because that's what we usually do when we done a design like that one. You know, as an engineer, when we finishing a design like this board, the first thing we want to do is checking on the EMI, or we just simply, you know, check on the eye picture. Yeah, here's a logic, bird eye scope. That's what we want when we want to analyze the digital data. That's all we want to do. And for the game, I think they can really do something, do some simulation on this database. Okay, let's talk more about it. I would like to talk more specifically, like the RF frequency, like your radio signal, like your normally the VHF, UHF, or even it's your let me think about it. It's called data link, like the link 4, link 15. They rather running rather on the protocol like the RGMII or the MDI, and they using a PHY integrated circuit and send it to the CPU. Send it to the CPU of the flight control system. That's the older one, because the modern one we don't really need to do that, because the modern one you can say, because we already integrated the file into the chip, like this one FPGA, like this one the silence from the silence, the K7 FPGA already have an integrated PHY logic loop here. Yeah, it was integrated from the PCS and PMA about the analog and the digital logic control. You can see, so what we want to do, like here, like for example, we want to send a strings. We want to send a strings to this data wire. So like what we do about it is make it to change it from the A bit to 10 bit. And after that, because the FPGA the GT transmitter, you have its own clock source. So the user interface have the different clock source with it. So first thing, phase adjustment. So that's what we want to do with. And after phase adjustment and the clock, and we finally can send out our data from the encoder, and then we can send it out to the PMI part, and PMI can send it through the data bus. And the polarizer, you don't really need to care about it, because the polarizer is about, if you mistake the TX as an RX, like the TXP and the TXN, you put it on the opposite side. It doesn't matter. You can flip it by setting up the APJS register. It's really easy. And because this thing with the because I mean the modem one we're using the GT transmitter. Yeah, that's the third is we're using most GT transmitters. The baseline the third is okay. Let's just talk about the GT transmitters. Itself has the fee. It has a fee layer inside of it, and it can be running at speed into 10 gigabyte. That's fucking insane. So you can now just transmit the raw video data to the data wire, because the modem one, like the data bus in your computer. Let's talking about design of your computer, right? You guys always know the PCI, right? The PCI E. Yeah, that's the most thing running on your computer, right? This one, if they have 40 lines, and each line, I will show you. So 4 gigabyte for 4 lines. So let's do a quick calculation about it. That means 10 x forward SRIO, or you just can call it rapid IO. X4. That's mean 10 of it. So it totally support how much? 40 gigabyte. On this data bus in the same time. Okay. That's I just give an example of the modern data bus, like the one in your computer. That's really fast, right? But here's a more faster thing, like the IPX, like the design I done here. Here. With the FPGA and DSP, we can pre-process the data. We can run the whole thing into like 80 gigabytes per second, or even more faster. Like you can just view the. Yeah, let's give VPX switch. each port 10 GB. That's the modem data bus. So that's the modem data bus work, because the modem one is no longer about this low baud rate input sources. Because for the modern one, we also need to combine a lot more complex data, because this thing is just a small little board. We just move it to the local bus, which is running at the baud rate like 30 Mbps. And for the modern, the modern data bus design is more like here. Oh, sorry. I would like to draw this thing again. I never tired about it. Oh, okay. If I remember correctly, it's like that. Two resistors and one capacitor on the middle. And then here they connect to the VSS, the ground. Because the model one, they have a more seriously data input. Like the graphic source. Like the graphic. Except, just like the one. Because you can see on the F35, for example, this is the F35. It actually have a lot of camera. But I just quickly draw that one. Just don't blame me for that one. Okay. On its back have a 4K camera, and then below its nose have a 4K camera, and here is a radar. Also take a lot the baud rate as the camera, and here's a numerous the infrared detector also being counted as camera. There's a lot of them at the edge of the aircraft, lots of them. So that's totally, you probably have over 20 or 20 more the graphic input. And I think that at least takes about 40 gigabytes per second. For the data bus. And all those things, they're all taking up the status. Yeah. It's the same about it. I think that's the most thing I want to talk about, the data bus. The reason I want to talk about data bus because all the devices of the aircraft is on it. I hope this video can help you understand what does the thing do, how they work. Okay, because I don't know. This one is a design I done it before about this VPX motherboard here. Oh yeah. Yeah, you shouldn't think it's too complex. It's just like your computer. You have your RAM and your disk. This is a disk, the MTF C4G LDDQ. That one is a 4 GB disk, 4 GB disk. Just like seeing your by just like this one, just like a SSD. Okay, just like this one. This thing does the same thing. It does the same thing. And what is this one? The MT41K512 megabyte. That's the RAM. That's the RAM. Like you call it DDR, but it's a DDR full name. I mean the DDR's full name. The RAM's full name is DDR3 SD RAM. That's the full name of this thing. And for the server or for the switch, and we always need to consider about how many let me yeah, you should take about you always need to counter how many LUT and AFF used in your FPGA. That means how many registers or how many gate you've been used of this CPU or FPGA or DSP. You always need to counter that, and based on this, to decide how many SD RAM you need to use. Okay. I think that's about it. Oh yeah, let's just finish it today. Oh, by the way. Simulations. I think I already told that. If they really want to make a real simulation, I think they need to design the board like the data bus board of the F35 once more to give an accurate EMI simulation. Giving an accurate EMI simulation. If they really want to do a simulation, if they're really taking serious about it, I think they can do such work. It will be really worth it. Because there's like how we lay out such board, we need to we make the data wire. They need to have the same length, so we made this thing. Just slope around like this one. Just make it all have the same length. This is for the data wire. This is a single data wire. The TX, TXP, TXN. Yeah, just like the same like that. All right, let's just finish today.